Direct current circuits are basic parts of electronics in radio, TV, computer, remote control, sensor, and other devices. The direct current components consist of direct current voltage supply, resistors, capacitors, diodes, and transistors. In this lesson, we concentrate on direct current circuits that are made up of direct current voltage supplies and resistors. Introduction. In this lesson, you will be able to define EMF and potential difference, understand electrical energy from the definitions of EMF and potential difference, use the formula power P equals I epsilon. Know that the sources of EMF have internal resistance and use the equation epsilon minus IR equals V. Understand the effect of internal resistance on the power supplied to a load. Click the Generate button. The flow of electricity around a simple circuit can be compared to a water flow system. What is the electrical equivalent to the pump, water-driven turbine, and the water itself? The battery is equivalent to the pump. The light bulb is equivalent to the water-driven turbine and generator. Charge is equivalent to the water. Can you suggest some reasons why? Click on each title to see the comparison between each system. Click on the switch to close the circuit. Cells are sources of electrical energy that cause charge to move in electric circuits. They have traditionally been called sources of electromotive force, but they are actually sources of energy, not force. That is why it is better to use the term EMF rather than the electromotive force. Click the definition of EMF button. In a circuit, 0.25 coulomb of charge gains 3.0 joules of energy from the cell. What is the EMF of the cell? Click the definition of potential difference button. Click on the bulb. When 1 coulomb of charge passes through this bulb, it dissipates 6 joules of energy. Use the definition above to work out the potential difference across the bulb. Answer: the potential difference is 6 joules per coulomb, or 6 volts. Click on resistor R, then click the power button to derive an expression for the power dissipated by the resistor. Click the power button to derive an expression for the power supplied by a cell. Calculate the power dissipated by the 20 ohm resistor in this circuit and deduce the power dissipated by the 10 ohm resistor. Summary: the EMF of a source is defined as the energy supplied to each coulomb of charge by the source to drive the charge around a complete circuit. Potential difference between 2 points in a circuit is the energy required by 1 coulomb charge to move between the 2 points. The units for both EMF potential are joules per coulomb or volts. power dissipated by a resistor equals voltage times current. Power output of a cell equals EMF times current. In this circuit, we have placed a high resistance voltmeter across the terminals of a dry cell. Click the switch to complete the circuit. What is the voltage across the terminals of the cell? Answer: 1.50 volts. Since the resistance of the voltmeter is very high, we can assume that this is the voltage across the cell when no current is flowing. This is a close approximation of the EMF of the cell. Now we have added a resistor to the circuit. Click the switch and measure the voltage across the cell again. Answer: the voltage across the cells is 1.35 volts, which is less than the EMF 1.50 volts. The difference of 0.15 volts is called the loss voltage. This is due to the voltage drop across the internal resistance of the cell. What is the combined voltage of 8 dry cells? Click the hands to short circuit the terminals. Answer: 12 volts. Now click on the lead acid battery and again short circuit the terminals by clicking on the hands. What do you notice? Answer: with the lead acid battery, a spark is produced. The voltage of the two power sources is both 12 volts. So why do the dry cells fail to produce a spark? Answer: the internal resistance of the lead acid battery is very small and hence a very large current of a few hundred amperes is produced when short-circuited. Click on each symbol in the circuit to see the potential difference. What is the expression for terminal potential difference V in terms of the EMF and lost voltage? Answer: terminal potential difference equals EMF minus loss voltage equals epsilon minus IR. This interactive model can be used to explore the effect of internal resistance in a circuit. What happens to the voltage across the load when big R is very large compared to R? Answer: the voltage across the load is almost equal to the EMF 1.5 volts. In this circuit, the internal resistance is fixed at 0.5 ohm. Alter the resistance of the load R and observe what happens to the power dissipated by the load. What do you observe? The power is a maximum when big R equals 0.5 ohm. Click the power button to work out an expression for the power dissipated by the load. Use the slider to increase the value of R and plot the corresponding power graph. When is the power a maximum? The power is a maximum when the resistance of the load equals the internal resistance, big R equals R. Is internal resistance useful to a battery? No. Internal resistance decreases the useful power of a battery. Battery manufacturers aim to minimize it to make batteries more efficient and longer lasting. Click on each part of the question to reveal the corresponding answer. Summary. The internal resistance of a cell is caused by the resistance experienced by the charge flowing through the chemicals in the cell. The internal resistance causes a decrease in the useful potential difference across the terminals of the cell. Terminal potential difference equals EMF minus lost voltage V equals epsilon minus IR. The power dissipated by a load is a maximum when the resistance of the load equals the internal resistance. Internal resistance decreases the useful power of a cell or battery. Battery manufacturers aim to minimize it to make batteries more efficient and long-lasting.